polarity is one of those concepts that a lot of people struggle with, and they struggle to understand what it actually means and how to get their head around it. It's a very important part of the course, however, because it directly links to the melting and boiling points of simple molecular structures. Because in order to correctly identify the intermolecular forces that are happening between simple molecules, you need to be able to decide or to work out whether a molecule is polar or non-polar. So in this video, I'm going to explain what we mean by polarity and how we apply that to bonds, covalent bonds, and to molecules, simple molecules. So the polarity of a covalent bond will all depend on the electronegativities of the covalently bonded atoms. If there's no difference in electronegativity, so you've probably got two atoms of the same element bonded together, then the electrons within that covalent bond, they're shared equally, because obviously a covalent bond is the shared pair of electrons. Now, as a result of this, we would say that the bond is non-polar. If we look at hydrogen as an example, so hydrogen is a molecule, and we write it as H2, which means we've got two hydrogen atoms bonded together. It's a diatomic molecule. If I was to draw the dot and cross diagram, it would look something like this. So each hydrogen is sharing an electron. So we've got the shared pair of electrons in between the two nuclei of the two hydrogen atoms. If I was to draw the displayed formula, then we just draw a line between the two atoms to show that it's a single covalent bond. Now, as I said, we've got two atoms of the same element here that are covalently bonded together. What does that mean? That means that the electrons within the covalent bond basically feel or experience an equal pull from either of the two nuclei. Okay, so the electrons in the bond, I'm just going to draw them on, are basically experiencing an equal pull from each nucleus of each hydrogen atom, because they're obviously the same atom. So what does that mean? That means that the electrons are just going to lie in the center of the two nuclei, because they're being pulled left and right with equal strength. So that basically means they're not going to move, and they're just going to lie directly in the middle of the two atoms. So the negative charge of the electrons is in the center of the two atoms. So that means there's no uneven distribution of charge of the electron density. So therefore the bond is nonpolar. This can also be described as a pure covalent bond because the electrons are being shared equally. Okay, so that means that the covalent bond is purely covalent. So they're being shared equally. Now, if we have two atoms that are different, bonded covalently, then there's going to be a difference, or there's likely to be a difference in their electronegativities. This means that the electrons within that covalent bond are going to be shared unequally. Okay, and this will result in a polar bond. A good example of this would be hydrogen chloride, so HCl. So dot and cross diagram would look something like this. So we've got that shared pair of electrons in the covalent bond. The displayed formula would be like so. Now, chlorine is actually more electronegative than hydrogen. And what does that mean? That means that the chlorine is pulling the electrons in the bond towards itself much more strongly than the hydrogen. So those two electrons in that covalent bond are actually going to be pulled towards the chlorine. So they're going to sit much closer to the chlorine atom than they are the hydrogen atom. Okay, and we know that electrons are negatively charged. So the negative charge, or the electron density, lies more towards the chlorine. This results in a polar covalent bond. And because the electrons are lying closer to the chlorine becomes partially negative because electrons have a negative charge. So those electrons are making the chlorine what we say partially negative. And to demonstrate that the bond is polar, we use something called partial charges. So if I was to draw the displayed formula of HCl again, knowing that the chlorine is more electronegative and the electrons lie more towards the chlorine, we would say that the chlorine is delta negative. Okay, so we use the little symbol delta and we use a little negative charge to show that it's delta negative. And we say that the hydrogen is now delta positive or slightly positive because the electrons are being pulled away from the hydrogen, which is leaving the hydrogen now slightly positively charged. And as a result, the hydrogen becomes partially positive. So the little delta symbols that I've used, these are called partial charges. And it's really important that we use these to show whether we think a bond is polar or not. So this would be described, that HCl will be described as a polar covalent bond. And we can actually use another term to describe the unequal or the uneven distribution of the charge. And this separation of charges is called a dipole. So you've probably heard that phrase before, dipole. It's very similar to partial charges, but we can actually use an arrow to show the direction of the dipole or the direction of the negative charge. So the arrow that I've just drawn here with a little line through it, that represents a dipole, and it's showing us the direction of where the electrons are lying more towards. So the dipole will point towards the more electronegative atom to indicate the direction that the electrons are most strongly attracted. And this is really important when we look at molecules and determining what kind of intermolecular forces are acting between those molecules. So the polarity of a molecule will depend on its shape and whether it contains any polar bonds. So let's have a look at a couple of examples. Let's have a look at water. So water's shape is non-linear. So if I just quickly draw then the non-linear shape of water, okay, so it looks like that. Now, I need to put partial charges on, so I need to indicate which bonds are polar and which atoms are delta negative or delta positive. And again, it's all to do with electronegativities. So we know that oxygen is more electronegative than hydrogen, so therefore the oxygen is going to be delta negative and the hydrogens are going to be delta positive because the electrons are going to be pulled towards the oxygen. Now I can show this by using arrows or the dipoles. So the electrons are going to be pulled towards the oxygen atom, like so. Now if we look at those two dipoles that I've drawn, we can see that the overall dipole is pointing upwards towards the oxygen. So the electron density is going to be lying up towards the oxygen, okay? What does that mean? Well, that means that this molecule is therefore polar. So if the dipoles are pointing in similar directions, the molecule will be polar because the electron density is going to be lying within the same sort of region within that molecule. And this is why it's really important you know your shapes, because you need to be able to apply this to the different shapes. Because if we look at carbon dioxide, for example, which is a linear molecule, so its shape is linear, if I quickly just draw carbon dioxide, okay. Again, oxygen is more electronegative than carbon, so the oxygens are going to be delta negative and the carbon's going to be delta positive. Now if I draw the dipoles on this time, so the electron's going to be pulled towards the oxygens from the carbon, so we're going to have a dipole pointing towards the oxygen on the right, and we're also going to be having a dipole pointing towards the oxygen on the left. So this time the electrons are being pulled in opposite directions, and as a result these dipoles will actually cancel each other out. So if the dipoles are pointing in opposite directions, they are opposing one another and they've basically cancelled each other out. So overall the molecule is non-polar. So even though it's got polar bonds, the carbon-oxygen bond is polar because there's a difference in electronegativities. When you actually look at the dipoles within the molecule, you can see that they're cancelling each other out. So we say that the molecule is non-polar, okay? Couple more examples. Let's have a look at fluoromethane. So fluoromethane is CH3F, and the shape is tetrahedral. So this is what our molecule would look like if it's tetrahedral. Now again, let's add in the partial charges. Let's identify which bonds are polar. Now, it's really important actually that you remember that the carbon-hydrogen bond, even though they're different atoms, we consider it to be non-polar. And this is because there's only a really, really small difference in electronegativity between carbon and hydrogen. So carbon and hydrogen bond is always considered non-polar. Okay, so try and remember that. So there's only one polar bond within this molecule, and it's the carbon-fluorine bond. Fluorine is the most electronegative element of the periodic table, so that's obviously going to be delta negative, carbon delta positive. Now, if I'm going to draw the dipoles on this time, there's only going to be one, and it's going to point up towards the fluorine. Okay, what does that tell us? That tells us that the electron density is lying up towards the fluorine, okay, or towards the fluorine. That means that this molecule is going to be polar because you've got one dipole and it's pointing in one direction, so there's nothing to cancel it out. So this molecule is polar. However, if we look at tetrafluoromethane, which is CF4, again, the shape is tetrahedral. So it would look like this. Now, each bond then, so each carbon-fluorine bond is going to be polar because fluorine, as I mentioned, is the most electronegative element. So the fluorines theoretically are going to be delta negative and the carbon is going to be delta positive. So with this time we've got 4 polar bonds. So let's have a look at where the dipoles are pointing. We're going to have one pointing up towards the fluorine at the top, and then we're also going to have 3 other dipoles pointing towards the other 3 fluorines. Now in this case, again, we can see that the dipoles, or the electron density, is being pulled in opposite directions. What does that mean? That means that they are opposing one another, and it means that they've essentially cancelled each other out. So tetrafluoromethane is considered to be non-polar. Okay, and then obviously you would use that information to determine whether it has van der Waals forces or London forces acting between the molecules, or whether it has permanent dipole-dipole interactions. So hopefully I've explained what polarity is and how we can apply it to bonds and how we can apply it to shapes of molecules. But obviously it's really important you learn your shapes, you know your shapes, so that you can identify whether the dipoles are cancelling each other out or not, and therefore determine whether something is polar or non-polar.